We started off impulse last week by looking at the change in momentum of a single object that was either speeding up or slowing down. Impulse was equal to m times delta v. It was also equal to f times t. And then we progressed to a situation where we had two objects. They were colliding or something like that. And we wanted to analyze that situation involving impulse as well. What we learned when we looked at that was that the impulse experienced by object A would always be equal and opposite to the impulse experienced by object B. We could analyze that problem the same way as we analyzed the early problems. Look at the initial and the final velocity of a single object and go with it. But we now had an option to look at the other object. The thing was, we had to make sure that we picked a single object, one object or the other, and go with it. Today, we're going to learn to analyze that situation where we have two objects colliding by looking at the system, not by looking at a single object, but by looking at all of the objects within the system. We're going to learn to use the law of conservation of momentum today. The law of conservation of momentum says this: in an isolated system, whatever that means, we'll talk about that in a second, in an isolated system, the total momentum will always remain constant. Now, you may find that the momentum of one object is increasing, the other object's momentum may decrease, but if you look at the momentum of the system, it will always stay the same. If we have an isolated system. An isolated system is a system in which there are no external forces. Give me an example of a situation where we have an external force. Like, what is an example of an external force? Something acting on the outside, something entering the system that wasn't there before. What's the most common one? We saw it a lot in Physics 20. It's the F word. Yes, of course, friction. What were you thinking, right? Friction. Friction is an external force. It can take away momentum from something, right? It can cause something to slow down. If we want to look at a system and analyze it using conservation of momentum, where the total momentum remains the same, we have to have an isolated system. In other words, we have to be analyzing the system before friction has a chance to do anything. Okay? No external forces, nothing to take momentum away, nothing to add momentum to this system. It's just the momentum of the two objects and the two objects only. Now, we can use this new law of conservation of momentum to analyze called collisions or explosions. A collision is self-explanatory, right? Two things bang into each other. Maybe they bounce apart, maybe they stick together, whatever. That's a collision. An explosion could be literally an explosion. Like a firework breaks into pieces or a bomb explodes. But it could be figuratively an explosion as well. If I'm on a skateboard and I jump forward, the skateboard goes backward. That was like me and the skateboard were basically one object before, and now we're two. That's like the bomb exploding into two pieces. We use it when we analyze collisions or explosions. But when we do that, when we look at that collision or explosion, we have to look at the momenta. Momenta is just plural for momentum, by the way. More than one momenta. The momenta immediately before and immediately after the collision or explosion. How come? Why is that word immediately so important there? Why do we have to look at the momentum just before and just after? The cars crash into each other. We don't want the momentum 5 seconds before the collision and 3 seconds after. We want a millisecond before and a millisecond after. How come? Yep. How come? Yes, it is still gaining or losing momentum. How come? If we look at 5 seconds before or 3 seconds after, there is a change in momentum in the system due to external forces. We have to have an isolated system where there are no external forces. The easiest way to do that is to look at the collision or explosion just before and just after, before these inevitable external forces have a chance to do anything. Yeah, is friction going to slow down these cars after they collide? Of course it is. So let's look at it just after the collision, before friction's had a chance to do anything. Does that make sense? Just before, just after, immediately before, immediately after, so that we have an isolated system. Now, just a little reminder from last week, like we're not throwing out this concept of impulse. When we're looking at two things colliding with each other, we know that each individual object will gain or lose momentum. That doesn't change. It still does. Like we still gain or lose momentum if we're looking at the individual objects. You understand that though, now we're looking at the system. The total momentum of the system remains constant. If the momentum of object 1 was plus 10, the momentum of, or the impulse, I should say, of object 1 was plus 10, then the impulse would be of object 2 would be negative 10. The total remains the same. Individually, we gain or lose momentum, but the total amount of momentum will remain the same. And that's what we're focusing on now, the momentum of the system, the total amount of momentum, as opposed to the momentum of each individual object. You might also remember that when we looked at impulse, we derived an equation for impulse that came from Newton's second law, F equals ma. Conservation of momentum comes from Newton's third law. And just like Newton's second law, that derivation you're not going to have to be able to do, but you do have to know that Newton's second law leads us to impulse, and Newton's third law leads us to conservation of momentum, even if you don't remember exactly how that happens. We're going to say Newton's third law, stated mathematically, looks like this. F12 is equal to negative F21. What does that mean in words? The force of object 1 acting on object 2 is equal and opposite to the force of object 2 acting on object 1. F12 would be m times a. F21 would also be m times a. Let's replace a with delta v over delta t. Notice I put these subscripts beside m and delta v, but I didn't put a subscript beside delta t. How come? Why did I not distinguish between the time of contact for object 2 versus the time of contact for object 1, Ben? Yeah, they interact for the same amount of time, which means that we can actually cancel that out, right? Leads us to m times delta v2. m2 delta v2 equals negative m1 delta v1. Look, the impulse of object 2 is equal and opposite to the impulse of object 1. Now let's think about that. If object 1 impulse is 10, object 2's impulse is negative 10. In other words, the total amount of momentum will remain the same. Pi will be equal to Pf. The initial momentum of the system will be equal to the final momentum of the system. Object 1 gains 10, object 2 loses 10, the total amount of momentum remained the same. This is the law of conservation of momentum. If you take a look at that physics principle sheet, the back of the room behind Anna, principle number 4 is conservation of momentum. We're going to use that a lot over the next several days. Principle 4, conservation of momentum. Okay, let's do one example and then we'll call it a day. Example number 1, it says a 1,500 kilogram car traveling north at 20 meters per second collides with a 1,700 kilogram car traveling south at 21. I'm going to circle that because we got a north-south thing here, directional thing, positive, negative. The two cars entangle. Entangle means they stick together. I wrote that down on my little dictionary thesaurus at the back of the room as well. Entangle, stick together, become one, head off as one. What's the velocity of the wreckage immediately after the collision? Now you understand that we could analyze this or try to analyze this using impulse. If we did, we'd have to pick an object and go with it. Either car A or car B, but not both. I'm going to choose to analyze this using conservation of momentum, this new thing that I just learned. And to do that, I'm going to analyze the system. Notice we do say immediately after, before any external forces have had a chance to kick in, right? So that we still have an isolated system. Write down some givens here. We're going to say M1 is 1,500 kilograms. M2 is 1,700 kilograms. There's a velocity here that's 20 meters per second. What is that? Is that V1 or is that V2? Object 1 or object 2's velocity? 1 or 2? What is it? Does this remind you of the eye doctor a little bit? 1 or 2? It is object 1, you're right. Is it V1I or is it V1F? The initial or is it the final of object 1? It's traveling at 20 meters per second before it collides. That's V1I, right? V2I, be careful of this one. V2I is negative 21 meters per second because this car is going south before the collision. Object number 2, car number 2, south before the collision. Now, the final velocity, we're just going to call VF. Anybody know why I didn't put V1F or V2F or something like that? Why did I just call it VF, Austin? Yeah. Like there's one object. If you want to call it V12, or even if you want to call it V3, I suppose, but we don't really need to because there's only one now. Remember how I stated the law of conservation of momentum, Pi equals Pf. There are two objects, each with momentum, object number 1 and object number 2, before the collision. After the collision, how many objects do I have? 1. So I'm going to call it M total times VF. One term because there's one object. Before the collision, there's two terms because there's two objects. If we have 14 things colliding with each other, then we'd have M1 V1I plus M2 V2I plus M14 V14I. Let's sub in some numbers here. M1 is 1,500 times V1I is 20 plus 1,700 times negative 21. Don't forget the negative. The combined mass is 3,200 kilograms, and we're looking for VF. This is 30,000. 1,700 times negative 21 is negative 35700. Combine these numbers, divide by 3,200, and we get a final velocity of, somewhere I have it here. Thank you, Jacob. Negative 1.8 meters per second. It is negative, means that, hey, we have one car going north, one car going south. Afterwards, the combined wreckage goes south, right? Make sense? Okay, here's your homework for tonight. Of course, you have quiz number 3 tomorrow, which is on force versus time graphs. In addition to that, you also have worksheet number 3. Worksheet number 3, only the first 2 questions on that worksheet. Got it? Worksheet number 3, questions 1 and 2.